Welcome back to the main session. So we are on with the next presentation. The next presentation will be made by Leonid KORELSTEIN. Leonid is VP of Research and Development at Piping Systems Research and Engineering Company, and also product manager of the CAPE part of PAS software, which is used for Hydra system piping fluid flow analysis. Leonid will give a short review of researches currently underway at PSRE on speeding up thermodynamic libraries usage using dynamic spline interpolation. This research is made in collaboration with Mendeleev University of Chemical Technology of Russia, where Maria Shkripashenko studies toward a PhD under the supervision of Professor Tomasz Gartman. Both are co-authors of this presentation. This research aims at decreasing the number of calls to thermodynamic libraries and may open additional perspective for use of third-party CAPE-OPEN property packages. Leonid, you are welcome.
Yes, thank you so much, Michel. Okay, and thank you for inviting me to present on CAPE-OPEN. So the agenda of this presentation is first a short introduction about what is Piping System Company and what is PAS software and specifically Hydra system software. And then several words about some history of our participation in CAPE-OPEN and CO-LaN. And then we will cover our topic. So about piping system is almost 30 years now, 30 years university, but in fact experience is much longer because the software that was develops for 40 or 50 years. And this is mostly analysis software for piping equipment, and we also are authors or co-authors of different international and Russian technical standards and guides for different kind of piping and equipment. And of course we are members of many known associations and organizations. And we have also many years of cooperation with leading plant design computer design systems and leading CAPE software vendors. And if you are interested, just look at our website, www.password.com. So about this, our software, which is so on international market, it has a brand PAS, Piping Analysis and Sizing Suite. It consists of mainly two parts. It has the part of piping and equipment stress analysis, but we are now interested in its process engineering analysis, which consists of three software programs. But main program is Hydra system for piping flow analysis, for pressure drops and heat losses, and two other some kind of variants, yeah, of it, for pressure relief system analysis and for thermal insulation design and sizing. So if we look at these three software, it's in fact one software with a software structure very similar to what CAPE-OPEN use. So it's some kind of PME and different libraries like for thermodynamic libraries, piping network solver, different kind of database for climatology data, salt properties, piping material properties, insulation material properties, and so on. And of course some service functions like report generator. So how this looks like? So this is just some screenshot from interface. And so Hydra system is piping network flow analysis, commercial software, which several thousands of users. And our primary focus was and still remains process piping of all kinds, but it's also are used for different kind of municipal networks, outdoor gas networks, heat and water networks, and also for oil and gas field gathering system. So we try to provide some tools which would be useful for any process and piping engineer. What it can do? So all kinds of steady-state flow analysis and complex piping system, including flow distribution, pressure drop, heat exchange with environment. It could cover real liquids and gases. It could cover multi-phase flow, including taking into account different flow patterns for gas liquid, including vaporization, condensation, gas three-phase. This is important for field pipelines like gas, oil, water, fluids, and also some recent development is slurry flow and some parts of flow assurance. And of course, choked flow, especially for multi-phase gas liquid flow, water hammer, and different opportunities for sizing and optimization, like diameter selection, centrifugal pump sizing, control well for safety valve sizing, and so on. And of course, different kind of different features for integration, including integration with different computer design systems, and our own piping stress analysis, of course. No, just several screenshots to show how that would be. You can quickly calculate, you can see flow patterns on different, map of flow patterns, for example, on different piping and so on. Okay, now about our relations with CAPE-OPEN. So we are members of CO-LaN for already 10 years. And we also have a long cooperation with several active members of CO-LaN. Of course, first of all, ProSimSA. And we are distributors of ProSimSA in Russia and use their software. And we also have some relations with rural university. We use JERC. 2008, we are members of Tulsa University Fluid Flow Project. And in Mendeleev University, we deal with HEM stations for many years. And Lind Engineering is also one of our users. So we was very interesting in CAPE-OPEN, and our leading developers passed the CAPE-OPEN training in 2013. And we also was active participants of hydrodynamic SIG for natural reasons. So we had some plans to implement CAPE-OPEN in Hydra system, first of all. And the first priority was to have thermal interface and unit interface in Hydra system as PME, and then probably unit interface for Hydra system for PMC, for PMEs who just want to call piping network analysis, for example. But plan were delays because there was not enough demand from the market, and the task that was our first priority was implemented or by direct integration or by specific COM integration. For example, with similar thermodynamic and other thermodynamic package, or with space for centrifugal pump sizing. But now we are looking again, and we are very inspired with CoreBear progress. And so we are now going to reconsider our plans and look at Corge and return to this task to implement CAPE-OPEN and pass Hydra system. So one of the problems was why we delayed this implementation, because CAPE-OPEN integration looks complicated and time-consuming. And Corbia probably will solve partly this problem, but not completely. Because and here is another side of this problem. So we meet this difficulty, and I think that this difficulty is just common for many PME developers. So the more complex is our PME task and PME analysis, the more calls to some property package we need to do. And as far as we increase the power of our software, this number of calls start to increase astronomically. So, and especially this is the case when we have very complex analysis, like complex piping network with multi-phase, multi-component fluid, with heat exchange, and even with multiple choked flow in some places. So sometimes this number of calls for different phase equilibrium and thermophysical properties is up to million. Of course, and our analysis shows that in this case, the time for just properties of phase equilibrium analysis and the calls is 90% of the whole run time, sometimes even more. So of course, probably this number can be decreased by some reorganization of code and some optimal, but the problem still remains. So we need to radically decrease number of thermal PMC calls. How to do this? I think that everybody knows this trick, some kind of table lookup. So we need to do this, some kind of calculation, some kinds of calculation of our necessary properties and phase equilibrium in some point preliminary, and then try to build some approximation, which will provide engineering accuracy, which is needed for our PME. So the question is how to do this? How many points we need? How large should be the grid? And which specific approximation to use? And the task is that we have these parameters. Usually we use pressure and temperature, or pressure and enthalpy, or pressure with entropy. But it's difficult to predict in which specific region these parameters lay. We can do them preliminary estimation, but sometimes we meet the cases that, okay, we will cross a phase boundary and we don't know what to expect. So we need to build some interpolation, which could be very easily to extend if necessary, if the parameter region is extended. And when we do this rebuild, we should provide that the already calculated properties will not change, or at least will not change significantly. So what we should also take into account, we need this to be thermodynamically consistent. So there are thermodynamical relations between different thermodynamical parameters and properties, and we need our approximations to suit these relations, or even to use these relations effectively to build this interpolation, for example, to use them for calculation of derivatives. And there are also typical monotonic behavior, some parameters. We don't want our interpolation to be not monotonic, not physical. So we also need to take into account which type of fluid we deal with, from one component to multi-component to pseudo-component petroleum fractions. And also, what is the parameter region? If we are in liquid or in gas or in multi-phase or near the critical point, and also take into account some type of calculation, what specific list of properties we need, and what is accuracy is needed, and also some features of specific thermodynamic libraries, because we use several libraries, and our user can switch to any library if he would like to use. And depending on the features of this library, the interpolation and can be different. So depending on, for example, what parameters it supports, or can it calculate derivatives, and can it calculate derivatives analytically, or to what accuracy? Okay, so this is an interesting task, and I'm sure that many CAPE vendors do this internally, but this usually is keeping us know-how of the company. And we just looked to the literature. We found some literature, but it's surprisingly limited number of scientific articles about this. So we select this as a research topic for Maria Skripachenko, PhD in computer science and engineering. And what we would like to do, we would like to try to find, implement in program and publish some kind of universal approach how to do this dynamic interpolation, including, depending on all these factors. This should include optimal grids, how to build the grids, how to build, how to select, and what interpolation methods to use, and some accuracy estimation. So what should be the parameters and how large should be number of points in the grid. So currently we just on the first stage, we just made some initial testing, consider some maybe not so complex cases like properties on saturation lines and real gases and liquids. And of course, I will talk what is the result so far. But of course, any recommendations and advices will be highly appreciated. So what are we doing? We're trying to use Hermite-type spline interpolation, just not to rebuild our approximation when extending. We consider two types of these splines. This is piecewise cubic Hermite splines and also monotonic modified Akiva cubic splines. And we compare them just to understand the behavior with some classical type of natural, so not a knock to be precise, cubic splines. So far we use it, we do this all in MATLAB. And for two parameters, we use the same type of bicubic spline. And dimensionless parameters is reduced pressure and temperature. So far, sometimes we also try to use logarithm, so some rescaling for reduced pressure. The types of grid is so far uniform, or sometimes rescaling to uniform in logarithm scale. And we are also thinking about look at some roots of Chebyshev polynomial or some maybe more complex grids. PMS tested so far was ProSim Simulus Thermodynamics, our own STARS library, GERC 2008, and what is TeamPro? What is TeamPro is Russian thermodynamic library for EF97 formulation. And we're going to involve more Nistrev probe, of course. We also have access to CalCEP PVTC, and we will be happy to have access and try and test with some other thermodynamic libraries. So on the first phase, we tested more than 35 different one-component substance, and we tried to choose very different substances, inorganic, organic, including heavy hydrocarbons, polar and not polar, simple and complex with different molecules, and so on. And we also started to test some mixtures and start to test some petroleum fractions. So on the saturation line, we try to 4 and 10 grids, and results were, I can say, surprisingly good. So we usually we build this trial from triple point to critical point, so the whole piece of saturation line. And in the most cases, the error for 10 points was less than 1% for practically all properties, and typically it's even less than 0.3. There are several seldom cases when we have not so good results, so the error was larger than 1%, but in this case we just need to look carefully what we deal with. Maybe we need to exclude some small region near critical point, or rescaled the property and approximate logarithm of this property instead of property. This is especially when this property is increasing to infinite near the critical point. So this works practically in all cases. Just one example. This is an example with saturated weapon of all fractions versus temperature, and here is a spline, you see. And interesting that, for example, if you just use values, yes, you have accuracy of about 0.2, but if you use derivatives derived also from a thermodynamic package using Clapeyron-Clausius equations, the accuracy is already 0.01, much better. So for bicubic interpolation, here are the typical regions we'll look. And again, we use modified Takima splines and compare them with not splines. And we use uniform grid. Again, very small mesh size, in fact. And again, the results are very promising. So for mesh size of 10, so only 100 points, Makima produced the best results for liquid and subcritical gas, sorry. And for supercritical fluid, the best is spline interpolation, but Makima also produced very good results. And average maximum error is about 0.4%. There is some several cases when we meet some problems, but most of these cases are easily addressed by rescaling. And there are some 1 or 2 cases when we just need to check if the results of thermodynamic library is realistic. So the conclusion here is many words, but to talk short, this, yes, bicubic splines are working and provide very good accuracy. And we would recommend to use modified Akima splines in most cases for this purpose. And yes, this should really produce speed up, not just in times, but maybe in order, several orders. Okay, next steps which we are going to do is first test complex multi-component fluids, and also look into the same type of interpolation inside for two-phase mixtures inside gas-liquid envelope. And more complex task is how to deal with some regions where we have some phase diagram boundaries. And so we consider some kinds of interpolation in the regions with curve boundaries. And of course, the special case is interpolation near fluid critical point. Here we need just to take some known solutions, known behavior near critical points, and start from it, I think. And I would like to thank our VP of IT, Alexey Timoshkin, for his very useful assistance and recommendations while we do this collection of different types of interpolations. So that's all I would like to tell you. So any questions and any proposals? And yes, we think that this research, if successful, could be some part of some kind of add-on to thermo-CAPE-OPEN interface, because I think this is just a common problem for everybody.